So now that we have gone over and reviewed how to build a linear regression model, we are now looking towards making inferences for regression. And this is our culmination of everything that we've done. And this is to finish up Unit 7. So be mindful of the homework problems. I know you guys are keeping pace pretty well. These will be due the end of April. And our objective for this chapter, chapter 27, will be to determine the statistical significance of a least squares regression model. So this first section, we're going to be focusing on this one example that our book uses. So this example revolves around the relationship between percent body fat and waist size in inches. Here is a scatter plot of our data. And as I pull this up, this is looking at a study from BYU in the 1990s of 250 male adult subjects. And we are trying to understand the relationship and the association between waist size in inches and the percent body fat that each person had. And if we remember, in regression, we model the relationship between two quantitative variables, a predictor variable, or oftentimes called the explanatory variable or the x variable, and the response variable. So our response is our y that we're looking at. To do that, we create an idealized regression line, which assumes that means of the distribution of the response variable for each value of the predictor variable fall along the line with individual values distributed above and below the mean response value for the predictor. And those data values that fall above and below our least square regression line, what we can then find is the error or the residual. The fact is, we can always calculate a correlation. If you just generate two random lists of numbers, you're going to be able to produce a correlation coefficient. Additionally, with those random selected numbers that you can make, we can always create a regression model. So the question then becomes, is the model significant, or is it simply a function of sampling variability? And that's what we want to be able to tell with inferences. Is this data that we collected being able to be extrapolated towards our population, or could this just be happenstance with our sample and not representative of the entire population? So the purpose of regression model is to provide an idea of reality beyond just the data in our study. We want to be able to infer to this larger population. And so to accomplish that goal, these might sound familiar, but we test hypotheses and make confidence intervals about the slope and intercept of our regression model. Those are the things that we are going to be hypothesizing about and making confidence intervals. When we found a confidence interval for means, back in chapter 23, we could use a single statistic to suggest a single true underlying value for that mean of the population. Think back, this was what our one sample t-test was for means. And when we tested whether two means or two proportions were equal, we imagined that there was a true underlying difference. And we said that the difference was equal to 0, or maybe we're looking at the difference in proportions and we're hypothesizing that they were 0. There's no difference. But regression is different. So the question goes, what does it mean to do inference for regression? What does our model or this line provide us? And so there ain't no way, even if we know every population value, the data would line up perfectly on our straight line. And that's why we say all models are wrong, because all of our data is not on that line. So just picture this. In our sample of body fat, there's a whole distribution of just the percent body fat for men with 38-inch waists. So this distribution of percent body fat is for all men with 38-inch waists. But that's not the only waist measurement someone could have. They could have waist measurements of 30, 45. And so what we're looking for when we're modeling this is to find the distribution of every possible waist size. And it's continuous. So imagine if we had the distribution of percent body fat at different waist sizes. So we have 32, and it has its own distribution. And then we have 33 or 34, and each one of these distributions falls along our least square regression model. This is what we're trying to extrapolate and infer upon when we have our sample data to our larger population. So our model assumes that means of the distribution of percent body fat for each waist size fall along the line, even though the individual values are scattered above and below the line. So our model is not a perfect representation of how the variables are associated, and that's okay. And in fact, the model is usually wrong, but it will be useful. And we mean that it's wrong because the data values are not exactly on the line. If we had all of the values in the population, we could use the least squares methodology to find the slope and the intercept of an idealized regression line. So not just ours or our datas, but all of the datas put together. And we write the idealized line with Greek letters, just like when we talk about for populations. And we consider the coefficients to be parameters. So we're going to use beta naught, so that's the Greek letter beta, is the intercept, and beta sub 1 is the slope. And corresponding to our fitted line, we have y hat. This would be our regression line. Y hat equals b sub naught plus b1x. This would be our y-intercept, and this is our slope. Oftentimes, your calculator could also say y hat equals a plus bx, or mx plus b. And when we generalize this to our population, we get mu sub y, or the means of the response variable, equals the beta sub naught, or the population's y-intercept, plus beta sub 1, our slope of our idealized line, times our x value. Not all individual y's are at the means. Some lie above the line and some below. And so like all model, there are errors. And that's important to note. And we denote errors by the Greek letter epsilon. These errors are random and of course can be positive and negative. So if we want to figure out an individual score or an individual y value as opposed to the means, and we account for the error or the epsilon, when we add the error to our model, we can talk about the individual scores instead of the means. So all you need is beta naught plus beta 1 times x plus epsilon. And I would make a note of this formula. This is for individuals as opposed to the means. This equation is now true for each data value, since there is this epsilon, this error value, to absorb the deviation, and give a value for y for each x value. Like always, when we jump into one of these things, we have to check our assumptions and conditions. And when we talked about least square regression models in Chapter 8, when we fit lines to data, we need to ensure that the data is quantitative, sufficiently linear, and has no significant outliers. Now that we make inferences about the coefficients of that line, we are now required to verify more assumptions and thus check more conditions. So be careful about the order in which you check these conditions. And we're going to walk through the body fat percentage and waist size in a little more detail to show you these assumptions and conditions. If an initial assumption is not true, there's no point in checking later ones because we cannot continue. And finally, which I know some of us are avoiding, I'm going to say this again and again and again, but this is especially important for dealing with a scatter plot or a histogram of the residuals or normal probability plot. Draw a picture, draw a picture, draw a picture. It helps verify what you're doing, and it's not just mindlessly checking off a list going, yep, I did it, yep, I did it, yep, I did it. But by drawing it, you show your work. And that's the important part. When we check our assumptions and conditions, we can then use the technology, we can use the computer to calculate all of the values for us. So here we go. Our assumptions and conditions that we need to have met. So sufficiently linear, we start first. Examine the scatter plot for linearity. The shape must be linear, or we must straighten the data. And we've talked about that. We either take the log of x or the log of y or log both. And that goes to that circle from Chapter 9 if we're going up or down in terms of the power. If the scatter plot is straight enough, we can go on to some assumptions about the errors. So Make sure that your data is quantitative. We're not talking about counts. We're not talking about categorical data. The data must be quantitative for this to make sense. Next, with our independence assumption, we're looking for randomness, and we're looking for randomness in the residual plot. So the individual data values are randomly selected and provide a representative sample for our population. And we do this by checking the residual plot to see that there should be no pattern. So the residuals should appear to be randomly scattered. Next, we check our equal variance assumption, and we want to see consistent uniform spread, again, in the residuals. So check the residual plot. The spread of the residuals should be uniform. If you see some pattern emerging, either at the beginning or at the end, that is, again, something from chapter 9, a word of caution for us. So I think the book calls this, does the plot thicken? Then, if it's uniform, randomly scattered, and again, this is the residual plot, then we check our normal population assumption. So we check a histogram again of the residuals, and the distribution of the residuals should be unimodal and symmetric. And we have to check for outliers and gaps in the data. And we want to make sure if there are outliers, do they have leverage? If they have leverage or they have influence on our graph, then maybe we have to ignore or run both our plots with and without the outliers. If all 4 of our assumptions are satisfied, the idealized regression model will look something like this, where we have a distribution that fits a normal model at each one of these continuous measurements. So this would be waist size, 2% body fat. So at each value of the x, there is its own distribution of y values that follows a normal model. The fancy word is a bivariate normal. And each of these normal models is centered on the line and has the same, and this is the key part, the same standard deviation. Now you might be saying to yourself, we have a scatter plot, so we graph that. And if we're looking at the residuals, well, we had to fit a least square regression model to that to get the residuals. So what came first, our conditions or our residuals? And that's a good question. So as always with regression, the best way to check many of these conditions is with the residual plot, but we only get the residual plot after we compute the regression model. So we're going to work in this order. So number 1, make a scatter plot and we check for the linearity. If the relationship isn't straight, re-express the data. Otherwise, we're done. Stop, do not go ahead, do not pass go. 2, if the data are straight enough, then we fit a regression model and find the residuals. That's our E for residuals, and our predicted values. So that's our y hat. Next, we make a scatter plot of the residuals against the x or the predicted values. So this plot should have no pattern, and check in particular for any bend or inconsistent variation or any outliers. And those are our keys to see, does the plot thicken at all? If the data are measured over time, plot the residuals against time to check for evidence of patterns that might suggest they are not independent. So that's just a special case to make sure that if you're comparing things to time, this is what we need to check. If the scatter plots look okay, then we make a histogram and or normal probability plot, again, of the residuals to check that the residuals are sufficiently unimodal and symmetric. And if you're like, what? This is our new piece. So if all of these conditions seem to be satisfied, then go ahead with the inference. So we're going to stop here. We're going to walk through this example of checking the assumptions and conditions, and that will be the end of the first video. So let's run through our example on body measurements of these 250 adult males. So this study, conducted in the 1990s, was done by the BYU Human Performance Research Center, and we want to understand the relationship between percent body fat and waist size. So what they did is, from their 250 adult male sample, we have our scatter plot. What we need to do is check our assumptions and conditions prior to running any testing. So we have our quantitative data, and we need to first check our straight enough condition. So is our scatter plot straight enough? And there's no obvious bend in the original scatter plot of the data or in the plot of the residuals against the predicted values. We'll look at the residual plot in just 1 second. We also need to check the independence assumption. So these data are not collected over time, so we don't have to compare the residuals to time, and there's no reason to think that the percent body fat of one man influences the percent body fat of another man. So then we look at the residuals, and both the residual plot as well as a histogram of the residuals and the normal probability plot. So neither the original scatter plot nor the residual scatter plot shows any changes in the spread of the line, which is good. The nearly normal condition and outlier condition, our histogram of the residuals is unimodal and symmetric, as we can see. The normal probability plot of the residuals is quite straight. So we don't see any outliers coming from our normal probability plot, or NPP, indicating that the normal model is reasonable for these errors. So under these conditions, a regression model is appropriate. And this is what it's going to look like for the computer output for the regression. So it's going to say what our dependent variable is. So let's just outline this. This is going to be our y, or dependent variable. This is going to be our response variable. And down here, this is going to be our explanatory variable, or our x. We get our r squared, which is 67.8%. We get our standard error of our residuals at 4.713. And we get our degrees of freedom of 248. Now we'll get to this in a second, because this is going to be a little different than before, where we have our sample size of 250 and we're going to subtract 2. This number s, or s sub e, as we've seen before, will come into play later on. We also get our y-intercept of negative 42.73, and we get our slope. So this would be our b naught, and this would be our b1. So if we wanted to write out our estimated regression line, we would say our body fat percentage hat, or predicted body fat percentage, is equal to negative 42.73 plus 1.7 waist. So as waist goes up, body fat percent also goes up. Generally, we also look at our r squared for the regression is 67.8%. Waist size seems to account for about 2/3 of body fat percentage variation in men. The slope of the regression says that the body fat percentage increases about 1.7% points per inch of waist size on average. And again, squishy words. The standard error of about 0.07, and this is our standard error in our explanatory variable. Our standard error for the slope is much smaller than the slope itself. So it looks like the estimate is reasonably precise. And this is what we're going to get to in just 1 second. And there are a couple of t ratios and p-values given. So we have t ratios for our y-intercept and our x-intercept, plus we have p-values that are both almost smaller than 1, or smaller than 0. Because the p-values are small, it appears that some null hypotheses can be rejected. And these are the types of things that we want to learn how to formulate. So this is the type of work that you have to check prior to doing your analysis. What we need to look at now is more about what's our intuition about regression inferences, and what are we looking for when we're looking at the true sample model of slopes.